Hi everyone, this is the 8th lecture of this control system series, and let's see what we are going to discuss in this lecture. First, we are going to discuss about stability. Second, stability based on the location of poles. And last, we are going to discuss very few points about Routh Hurwitz stability criteria, and we will understand about one special case, and the rest special case will be done in the next video. Okay, so without any delay, let's start. Stability. Okay, so now let's understand what is stability. A system is called stable if the output of the system is bounded. Means we can call a system stable only if the system output of the system is being settled to a specific point with time, and if it's not being settled to a point, it's moving away from the point up to infinity, then the system will be called as a unstable system, not a stable system. Okay, अभी इसको मतलब डायग्राम से देखेंगे. We will see it with the help of diagram at how a stable and unstable system look like. Second point is the bookish definition. The response of the stable system must be completely integrable. Okay, it means that it should give a finite value if we integrate the response within the limit 0 to infinite. Okay, it should be less than infinite, then the system will be called as stable. Mathematical representation of stable system is given by this. And now let's see what about the graphical representation. So as you can see, this system and this system, we have two systems. One system is being settled towards a point with time. It is being settled, okay, toward this point. And the another one is the response of the another system is moving away from the point. Let's see, this was the point, and the response with time is moving away, and it is going up to infinity. So the first one, that this system will be called as stable system, and this one will be called as unstable, because the response is not being settled to a point, and in this case the response is being settled to a point. Okay, so I hope this thing about stability is clear to you. And now let's see how stability is based on the location of poles. अब अगली चीज हम लोग ये देखते हैं कि स्टेबिलिटी जो है लोकेशन ऑफ पोल्स पे कैसे डिपेंड कर रही है. ठीक है, टू अंडरस्टैंड दिस, लेट्स टेक अ सिंपल ट्रांसफर फंक्शन a upon s plus 3. So here the pole is minus 3. S plus 3 equal to 0, so s equal to minus 3, so pole will be minus 3. So it on pole 0 plot or s plane, it will be located as this one, minus 3. This part, let me just highlight it. This part is called the left half of the plane. Okay, and this part is called the right half of the plane from this line. If we move leftward toward this line, it will become left half of the plane, and rightward toward this line will become right half of the plane. So pole in this case lying in the left half of the plane. So now let's see what is the Laplace inverse of this one. Laplace inverse of this is given as this e raised to the power minus 3t ut. As you know, I have given you the Laplace transform of all this. So the graphical representation of this term will be given as this e raised to the power minus 3t. E raised to the power minus t, as you know, the graph is given as this decaying graph. So as you can see that this graph is settling towards 0. This graph is settling towards a point. So this system is stable. Okay, so this system is stable. Now let's see another one, like this one. Okay, and the location of poles for this one is given as this, as we have studied in the time response chapter. The location of poles for this is given as this. Now let's see the Laplace inverse of this. Laplace inverse is given as e raised power minus 40 sine 5t ut, and the graphical representation of this time domain function is like this, decaying function. So as we have seen in the previous slide, and that this type of system was given as unstable system because it is settling towards a point. So this system is also a stable system. So here we can conclude that if the poles are lying on the left hand side of the S-plane, if all the poles are lying in the left side of the S-plane, left side, so the system will be given as a stable system. Now let's see what will happen if the pole will lie on the right hand side of this plane, this side. Okay, let's see. A upon S minus 3. To show that pole will reside on right side, here I have taken S minus 3. Okay, so S minus 3 is equal to 0. So S will be given as plus 3. So the pole will reside like this. This is the right half of the S-plane. So pole is residing here on the right half of the S-plane. So now let's see what will be the Laplace inverse of this system. The Laplace inverse is given as this thing, where this will be positive instead of negative. So the graph for this Laplace is given as this. As you can see, the graph is approaching to infinite, and we already know that if a thing or a response is approaching to infinite, the system will be given as a unstable system or called as a unstable system. ठीक है, एक बार हिंदी में समझते हैं इस चीज को. जैसे हम लोग ने यहाँ पे सिस्टम लिया है जो S-3 पोल्स, मतलब जिससे कि राइट साइड पे लाई करें. ठीक, यहाँ राइट साइड पे. तो अब इसमें क्या करेंगे कि जैसे S-3 हो गया, तो अब पोल्स यहाँ पे राइट साइड पे पड़ गया. अब देखेंगे कि इसका रिस्पॉन्स क्या है. तो रिस्पॉन्स देखने के लिए हम लोग इसका क्या करते हैं, लाप्लास इनवर्स लेते हैं. लाप्लास इनवर्स लिया और फिर इसके जो लाप्लास इनवर्स है, मतलब जो टाइम डोमेन का फंक्शन है, उसका ग्राफ प्लॉट करते हैं. तो उसका जो ग्राफ है वो इनफाइनाइट को अप्रोच कर रहा है, और जो हमारा पोल जब लेफ्ट साइड लाई कर रहा था तो हम लोग देख रहे थे कि 0 को अप्रोच कर रहा था, यहाँ पे जा रहा था. ठीक है, तो जब इनफाइनाइट अप्रोच करता है कोई चीज, तो सिस्टम जो है हो जाता है अनस्टेबल. So the system, this kind of system is given as unstable system. Now let's see with another example. 25 upon s square minus 8s plus 25. The poles of this is given as this. Similarly, as we have taken in our previous example, in which the poles were residing on the left half, here due to this minus, poles will be residing on the right half. Okay, so the Laplace inverse of this response is this, which is that in time domain, and the response graphical response of this time domain is given as this thing. And we have seen in many of our examples that this kind of response is always unstable. And why it is unstable? Because the response is approaching to infinite. As you can see that response is approaching to infinite. That's why this type is unstable. Okay. So we have seen that if the poles are residing on the right half of the plane, okay, then all the systems are being unstable. So here we have a generalized thing that if poles are residing on left half of the S-plane, the system will be given as stable. And if any one of the poles is on the left side, the system will given as unstable system. Let's see that in the form of theory. Okay, if all the poles are located in the left half of the S-plane, the system will be stable. For stability, there is a condition that all the poles should be located in the left half. not a single pole should be in a right half of the S-plane. Okay, if a single pole will be on the right half of the S-plane, the whole system will become unstable. So all the poles should be on the left half. Okay, and another one, if any pole or poles, means single or multiple poles, are located in the right half of the S-plane, the system will be unstable. तो इसका मतलब है कि अगर एक भी पोल हमारा राइट साइड में चला जाता है ना, मतलब एक भी राइट में चला जाता है, तो सिस्टम तुरंत ही अनस्टेबल हो जाएगा. ओके, नाउ लेट्स सी व्हाट विल हैपन इफ पोल्स विल रिसाइड ऑन दिस लाइन, द लाइन ओनली, और in other words we can say that poles are purely imaginary. In that case, what will happen? Let's see. Here I have A upon S, which is a Laplace transform of unit step function. Okay, so it is a unit step type response, and the poles of this is given as is at 0, s equal to 0. So it is residing at this line, So the Laplace transform of this is ut, as I have already told you just now, and it is given as this. So as you can see that this is neither approaching to infinite nor decreasing. It is having a constant value. Let's say 1. Okay, so it is having a constant value. It is neither increasing up to infinite nor getting back to 0. So whenever this type of function appears which have a constant value, then these type of systems are given as marginally stable system. Okay, so if the poles will reside on this line, so the system will be given as marginally stable system. Please remember this. Now let's see with the help of another example that if the pole will reside on this line, then also will be the system will be marginally stable or not. So now let's take the Laplace inverse of this. It is given as sine omega t ut. So as we all know that graph of sine is given as this, a pulsating type, and in sine graph there is a maximum value and a minimum value. Okay, by which we can say that this graph is also neither approaching to infinite nor reaching to 0. So it is remaining constant between two values and keep oscillating between them. So this kind of system is also called as marginally stable system. ठीक है, एक बार इस चीज को हिंदी में बताता हूँ. देखो, जैसे कि ये जो लाइन है, अब हमें देखना था कि इस लाइन पे अगर पोल पड़ेंगे तो क्या होगा. तो यहाँ पे पहले हमने देखा कि s इक्वल टू 0 पे इस लाइन पे पोल पड़ा, तो ठीक है. अब इसका जो रिस्पॉन्स है वो कुछ इस तरीके से आता है. अब रिस्पॉन्स ऐसा है कि ना इनफाइनाइट जा रहा है ना 0 जा रहा है, मतलब एक कांस्टेंट वैल्यू पे सेटल रह रहा है या यहाँ पे ऑसिलेट कर रहा है बिटवीन टू वैल्यूज. ठीक है, कोई एक वैल्यू अप्रोच नहीं कर रहा, ना इनफाइनाइट ना 0. ठीक, तो उस तरीके के सिस्टम को हम लोग कहेंगे मार्जिनली स्टेबल सिस्टम. नाउ लेट्स सी अनदर एग्जांपल फॉर दिस. अनदर एग्जांपल इज a upon s square, which is the Laplace of unit ramp function. Okay, as we already know, and the location of poles will be given as s equal to 0 and s equal to 0. There will be two poles. There will be two poles on s equal to 0, or this type of case we say repeated poles. Two poles or repeated poles. For this type of case we say repeated poles. मतलब कि एक से ज्यादा पोल्स होंगे, एक ही जगह पे एक से ज्यादा पोल्स होंगे. अब इसका जो है लाप्लास टाइम डोमेन देखते हैं कि क्या होगा. TUT, टाइम डोमेन ऑफ इनवर्स ऑफ 1 upon s square is TUT, which is given as ramp function, and ramp is a straight line. Okay, this. Now as you can see that this line is approaching to infinite. This line is approaching to infinite. But as per our condition that if pole will reside on this line, the system will be what? Marginally stable. But let's understand this case. In case of repeated poles, okay, in case of repeated poles only, wherever we found repeated poles, ठीक है, अगर हमारे पास हम repeated poles होगा, whenever we going to find repeated poles, then the system will given as unstable, because as you can see that the response is approaching to what? Infinite. So it will be given as a unstable system. Remember this again. Whenever there exists a repeated poles, either on the left side, right side, or at this line, whenever exists repeated pole, the system will instantly become unstable system. Okay. So just remember this slide. This is very important concept that whenever exist repeated poles, the system will be unstable. Whether all poles are existing on the left half of the S-plane, it will be unstable if repeated poles are existing there. अगर repeated poles हैं तो हमारा किसी भी हालत में जो है सिस्टम स्टेबल नहीं होगा, हमेशा ही अनस्टेबल होगा. ठीक है. Now let's move on to next to understand our stability more clearly here. Absolute stability. Now what is absolute stability? The stability which is decided on the basis of location of poles. ठीक है. ऐसी stability जो कि लोकेशन ऑफ पोल्स के बेसिस पे डिसाइड की जाती है कि पोल्स के बेसिस पे हम कह दें कि स्टेबल है कि अनस्टेबल, वो स्टेबिलिटी जो है एब्सोल्यूट स्टेबिलिटी होती है. द स्टेबिलिटी विच इज डिसाइडेड ऑन द बेसिस ऑफ लोकेशन ऑफ पोल्स, that type of stability is known as absolute stability. Now let's see the definition here. Stability based on the location of poles, which gives us absolute stability. Okay. Now second is relative stability or conditional stability. It is based upon the analysis of gain margin, phase margin, etc. We will study these things later on. Okay. Here we are going to discuss in this chapter only about the absolute stability. So that stability which is given on the basis of gain margin, phase margin, etc. is relative stability. Okay, as you can see that stability based on the gain margin, phase margin, value of K will give the relative or conditional stability. So now we will move on to our next topic. Before moving to that, let's find out stability of some complex functions. Okay. Like this type of function, we have 4 poles here. We have to find the stability, absolute stability, by determining the poles that which are on the right half of the S-plane. Okay, and here we have order of 5 poles. So 5 poles are there in which we have to tell how many are in the right half and on the how many are on the left half, and on the basis of that we have to comment on the stability. Another one I have which have order of 6. So if we are going to find the root of this 5 order, 6 order or 8 order, something like that, it will become very lengthy, and frankly speaking we are like never going to make it right, never going to make it right, and if anyone does it, it takes a lot of time for that. Okay, so how to calculate, how to comment on the location of poles, how to comment on the stability? Let's understand what will be the stability of this. For determining stability of these kinds of higher order characteristics equation, this denominator, whole denominator is called characteristic equation. We use Routh Hurwitz criteria. Now let's see what is Routh Hurwitz criteria. Routh Hurwitz stability criteria. In this, suppose we have a system like this: GS, HS. HS is the negative feedback and GS is the open loop transfer function, as we already know about it. Okay, so overall transfer function will be given as GS upon 1 plus GS HS, and this red mark denominator 1 plus GS into HS is 0. Okay, for Routh Hurwitz we make the characteristic equation is equal to 0 for determining the poles of the system. So this whole term is called as characteristics equation. Okay, and Routh Hurwitz is a criteria in which without solving the whole equation, the number of roots which lie on the right half of the S plane can be calculated. मतलब कि RH क्राइटेरिया के हेल्प से हमें वो पूरे जो बड़े बड़े इक्वेशन है वो सॉल्व नहीं करने पड़ेंगे. बिना उसको सॉल्व किए हम ये बता सकते हैं कि कितने रूट्स राइट हाफ में है, कितने रूट्स लेफ्ट हाफ में है. ये सारी चीजें हम लोग कैलकुलेट कर सकते हैं. So now let's see how we are going to calculate the location of roots using Routh Hurwitz stability criteria. Let's start the calculation part. Here I have an example like this. So this denominator is called as characteristic equation, as we already knew. So now we will put up this whole will be equal to 0. Our first step, we have to put this equal to 0. Now we have to write like this: s raised to the power 4, then below that s raised to the power 3, then 2, then 1, then s raised to the power 0. And now here we are going to see the coefficients. Only coefficients matter. Like coefficients, we are going to have a0, a1, a2, a3, and a4. Okay. Now how we are going to write it? Now s raised to the 4, for s raised to the 4, we have to take only even terms here. And s raised to the power 4, 2, and s raised to the power 0. We have to take it in one row. Right? Okay. A0, then A2. Second term will be A2, and this will be A4 here. मतलब क्या करना है कि एक एक छोड़ के लेना है. 4 है, फिर 2, फिर 0. मतलब इवन वाले एक तरफ, ऑड वाले एक तरफ. Then for S3 we are going to write as A1, A3, and we have nothing for S minus 1, so we will write 0. So it will become for blank space it is considered 0 always in Routh Hurwitz. So A1, it will be A1, then A3, coefficient of 1. After 3 we will have 1 because it is odd, and then we have nothing, so we will have 0 here. ये इतनी बात समझ में आ गई कैसे लिखा गया. 4, फिर 2, फिर 0. 4 का कोफिशिएंट, फिर 2 का कोफिशिएंट, फिर 0 का कोफिशिएंट, देन 3 का कोफिशिएंट, फिर 1 का कोफिशिएंट, देन उसके बाद कोई कोफिशिएंट है ही नहीं, बचा ही नहीं, तो 0 लिख देंगे. ठीक है. नाउ लेट्स सी व्हाट वी आर गोइंग टू फाइंड इन अनदर रो. बस कैरेक्टरिस्टिक इक्वेशन का काम यहीं तक, इतना आ गया बस. ठीक है. Let's see, this term is given as b1, and the value of b1 is given as a1 into a2. Let me explain it how we are going to calculate b1. So here I have b1. Okay, and to calculate, for calculating b1, we are going to multiply a1 with a2, a1 with a2, then we are going to subtract a0 and a3, multiplication of a0 and a3. So multiplication of a0 and a3 will be subtracted. So as you can see that I have written here for b1, a1 into a2 minus a0 into a3, and divide by a1. Okay. And in another terms, you can write as minus of determinant of this one. Let me just erase it and tell you what determinant you have to take. Determinant of this whole thing. Minus of determinant of this whole term divided by a1. Okay, it will give you b1. Now what we are going to do for B2? For B2, we are going to hide this. We are going to completely hide these terms, this line, the above line, and we are going to do the same calculation as we have done for B1 with A1 into A4 and A0 into 0. Okay, so B2 will be given as A1 into A4 minus A0 into 0 upon A1. If we are calculating B1 or B2 or B3, it will always be divided by this A1. Okay, now let me erase this all. Now we have C1. In the same way, for C1, we are considering these four terms. These four terms in the similar manner. B1 into A3 minus A1 into B3. Or you can say that minus of determinant of this divided by B1. So it will give you C1. Okay. Now for C2, we are going to hide this, hide these two, and here we have 0 only because here are 0, so 0 0. So it will become B1 into 0 minus A1 into 0 upon B1. So it will become 0. C2 will become 0. Okay, now we will come to 0. As you can see that B1 into 0 minus A1 into 0 upon B1, that will give you 0. Now we will come to D1. What will be D1? This term will be 0 here because here are 0, so this will also be 0. Now D1. In the same way, we can calculate D1 by taking these four terms. C1 into B2, B1 into C2 upon C1. So D1 will be given as this. B2 into C1 minus B1 into C2 upon C1, or minus of determinant of this whole function, determinant of this. So it is B2. Now let's see how we are going to comment on the location of poles and stability regarding this Routh table. This is our Routh table. This whole table is our Routh table. So we have our Routh table given as this. In the previous slide, we have created our Routh table given as this. Okay, in the original numerical, you will get the values here, like 1, 2, 3, etc. Numerical values will be here. So it will be easy. Right now, I am just explaining how to do the calculation. So it seems a type of lengthy, but it is not. In the numerical, you will get numeric values instead of A1, A2 or something like that. You will get numeric values. So now let's see how the stability calculation or the location of poles calculation is done. So let's consider this first column. Okay, let's consider the first column, only the first column. Okay, so if we have in the first column, if we have sign changes, by sign changes means if we have plus term, minus term like this. So if we have any kind of sign change in the first column, any kind of sign change, single sign change, that will lead to the system to instability, or the system will be unstable. Okay, if any sign change in the first column, then the system will be unstable. तो मतलब कहने का है कि अगर पहले कॉलम में कोई भी साइन चेंज होता है तो सिस्टम जो है अनस्टेबल हो जाएगा. ठीक है. एंड अनदर वन, द नंबर ऑफ साइन चेंज, मतलब जितने भी साइन चेंज होंगे, द नंबर ऑफ साइन चेंज हमें काउंट करना होगा, वो 1 2 3 करके. will be equal to the poles on the right half of the S-plane. ठीक, number of poles in right half will equal to the number of sign changes in first column. ठीक, सिर्फ फर्स्ट कॉलम की बात होगी, सेकेंड थर्ड को कंसीडर नहीं करेंगे, वो सिर्फ कैलकुलेट करने के लिए है, अदर एलिमेंट्स उसको कंसीडर नहीं करेंगे. ठीक है, सिर्फ फर्स्ट कॉलम की यहाँ पे बात होगी. तो देखते हैं कुछ केसेस. सपोज वी हैव अ केस लाइक दिस. Here we are getting a sign change. So now let's see how many number of sign changes are here. To count the sign changes, here see plus, plus, minus, plus, plus. From plus to minus, here is one sign change. Let me mark it. Here it one sign change. One sign change. And from minus to plus again. Here again is a sign change. So let's count this red one. How many number of times we are getting this red? From plus to minus 1, from minus to plus 1 again. 1 plus 1. 2 sign changes are here. And according to our condition, if a single sign change occur, then the system will become unstable. So the system here is unstable, but the number of poles on the right half is equal to the number of sign changes. So the number of sign changes is 2. 1 here and 1 here, 2. So the system will be unstable and the poles residing on the right half will be equal to number of sign changes. So it will be equal to 2. RHS poles, I'm writing it in short, RHS poles will be equal to 2. Now let's see another case. Before that, just let me just erase this. Another case, we have this. And here I'm getting plus, plus, minus, minus, minus. So the number of sign change here is plus to minus, then minus, minus, minus. No sign change. Here no sign change. Here is one sign change. From plus to minus, plus to minus. So one sign change is here. So number of poles on the right half will be 1. And because we have one sign change in here, so the system will be unstable. So the system will be unstable, and due to one sign change, the RHS poles will be 1. Okay. Now let's see a simple numeric example that how we are going to calculate it for real. This one is for understanding purpose. Now let's see a numeric example. Here we have this characteristic equation is given as s cube 4.5 s square 3.5s plus 1.5 is equal to 0. Now for, as I told you, we are going to write it as s raised to the power 3, below that s raised to the power 2, then 1, then s raised to the power 0. Okay, now let's write the coefficients. Here the coefficients of s cube is 1, so 1 will be given. Then the odd one is 1 s raised to the power 1. The coefficient of s raised to the power 1 is 3.5. So we will write 3.5 here. And now we will move to s raised to the power 2. So the coefficient of this is 4.5. So we are going to write 4.5 here and 1.5 here and 0 here. We are getting 0 over here. Okay. So now let's see about this term. What will come this at this place? Okay, for this place, as I've told you, I have to take the minus of determinant of these 4 terms, minus of determinant of these 4 terms divided by 4.5. Okay, so minus of determinant, or I am taking it from the inverse side, which is 4.5 into 3.5 minus 1 into 1.5 upon 4.5. By calculating it, we are getting 3.16. You can calculate it. Okay, you will get 3.16. So here we will get 3.16. Now for this term here, we have to ignore these 2 upper values and multiply it by this. And we have 0 at both the places. We have 0. So this will be 0. So no need to write this, or you can write this or left it blank. You can do whatever. So it will become 0. And now for this here, we will have 3.16 into 1.5, 3.16 into 1.5 minus 0 into 4.5 divided by 3.16. So it will become 0 and 3.16 will get cancelled out. So, and we will be remaining with 1.5. So here will be 1.5. Okay, 1.5. So now let's see the first column here. See the first column here. Do you guys see any sign changes in the first column? No. No sign changes. So all the poles are residing on the left side of the S-plane, and the system is given as a stable system. So it will be stable and all the poles are on the left hand side. So RHS poles will be 0. Okay. Now let's see another example. This. From now we have a characteristic equation which is given as the denominator equal to 0. So denominator is this. So we will make a characteristic equation. The whole denominator will equal to 0. This is the characteristic equation. And now we are going to write it systematically in the Routh table. First, we have the highest order s raised to the power 5. So it will be s raised to the power 5, 4, 3, 2, 1, and 0. Okay. So now we have to write coefficients. So its coefficient is 1. Then another odd term coefficient is 2. Another odd term coefficient is 5. Another odd term we don't have any, so it will be 0. So 1, and then 2, then 5, then 0. Or we don't have to write 0. Then the coefficient of 4, 2, and s raised to the power 0. So 1.5, 4, and 10. Now let's see what we are going to get here. Here 1.5 into 2 minus 1 into 4 upon 1.5 minus 0.66. Okay. And now for here we have to ignore this and multiply these four, 1, 5, and 5, 10. 1.5 and 5, 10. 1.5 into 5 minus 1 into 10 upon 1.5. It will be given as minus 1.66. And here this will be 0. Now let's see what we will get here. For calculation of this place, we have to consider this, and this, these four terms. And we have to multiply it in a systematic manner. For minus 0.66 into 4, minus 1.5 into minus 1.66 upon minus 0.66. This one. We will get 0.227 here. And for here, we have to cover up this one and multiply 0.66 minus 0.66 into 10 minus 0 into 1.5. We will have 10 over here. And for this term, we have to consider these four and multiply these two minus these two upon this. Okay. So we will get 27.4. And for here, this place we have to ignore these two terms, and here we have both the terms 0, so it will be 0. And now for this term, it will become 10. How this will going to become 10 and how I calculated it so fast, let me just tell you. If the last term, or here you see here a 0, this term will always be equal to this term. If you see a 0 here, then this term will always be equal to this term. Remember that. That was happened in case of here also. This term was 0 and 10 was here. So this term will become 10. And now the similar case is happening there. So it will become 10. We can calculate it also, but we will get the similar thing because it is going to multiply by 0. So there is no meaning of this term. And after multiplying this, we are going to divide it by this term also. So it will remain with 10 only. Okay. Now let's calculate what is the stability over here and what are the location of poles. So as you can see that here is a sign change. A sign change means the system is unstable. In the first column there is a sign change, so the system is unstable. And now how many sign change is there? It is plus, then minus, then one. So one sign change. From minus to plus, then two sign change. So number of sign changes are 2. दो बार sign change हो रहा है. So the location of right hand side, number of right hand side poles will be 2. RHS poles will be 2 and system will be given as unstable system. Now let's see another example. Now we have this characteristic equation. Now let's write it in a Routh Hurwitz table form. S5, then 4, then 3, 2, 1, 0. Okay. Now let's write down the coefficients. 1, then 2, then 11, then 0. 1, then 2, then 11, then 0. Okay, we are not considering 0 here. Then s to the power 4 is 1, then 2, then 10. Okay, now let's count this value. For this value we have to take 1 into 2 minus 1 into 2 upon 1. So 1 into 2 and 1 into 2. 1 into 2 minus 1 into 2. 2 minus 2 will be 0. Okay, 2 minus 2 will be 0. So this term will be given as 0. So a 0 is neither a positive number nor a negative number. So how we are going to comment on the stability and how we are going to calculate the other values here. Okay, so we'll understand that. Now let's calculate this value. This will become 11 minus 10 upon 1. It will become 1. Okay, and this will become 0 again. So now if we have 0 only in the first column, then we have to assume 0 as a small positive number, epsilon. Let's say epsilon. 0 is assumed as a small positive number, epsilon. Okay, it is given as epsilon. Let 0 equal to epsilon. Epsilon is nothing but a small positive number. We have to consider 0 as a small positive number. Okay, and we have to replace 0 by this epsilon. Now we are going to calculate next value by the similar way we are doing it, and that is 2 into epsilon minus 1 upon epsilon. It will be 2 into epsilon minus 1 upon epsilon, 2 epsilon minus 1 upon epsilon. Let's put up the value here. Okay, it is 0. It will become 0 minus 1. So it is minus 1 upon 0. It will become minus infinite. So this will become minus infinite. And we are not considering infinite also. I'm just showing you that it is giving us as a minus sign. For further calculation, we have to consider this value, this 2e minus 1 upon e, epsilon, sorry, not e. Okay, we have to consider for calculation purpose, we have to consider this value. And for location, we have to consider only minus infinite. We are considering minus infinite. Now the second value will be, as you can see that 0 over here, so this value will become 10. Okay, now we have to come over this value. This will become this value into this, that is 2 into minus epsilon upon epsilon into 1 minus 10 epsilon upon this value, upon this. So after calculating, we will get here as 1. So it will become 1. And here we will have 0. And here we will have 10 because 0 we have over here. So as I have told you the trick that if we have 0 over here, then this value is equal to this value. So here we have 10. Okay. Now let's see the stability. We can easily say the system is unstable because we have a sign change in the first column. We have a sign change in the first column. We have a sign change. Actually, we have two sign changes from here, plus to minus and minus to plus, 1 and 2. प्लस टू माइनस एंड माइनस टू प्लस, प्लस से माइनस हो रहा है एक साइन चेंज, फिर माइनस से फिर प्लस हो गया तो दो साइन चेंज. सो नंबर ऑफ साइन चेंजेस इज 2. So the system is unstable and the poles that are residing on the right hand side of the S plane are 2. Okay, the system is unstable and the poles which are on the right half are 2. So now let's see what we are getting, or what is the conclusion if we are getting only a single zero in the first column. We will study if we get the whole row as a zero. We will study that in the next lecture, but now let's see here that if we get a single element 0 in the first column, single element will be 0. What does it mean? Okay, the conclusion. So now let's move on to that. Okay, it means two things: either equal and real roots of opposite sign, okay, or pair of pure conjugate imaginary roots. Pair of pure conjugate imaginary roots. Okay, so this is given as this thing. Either the root will lie on this line of equal and opposite sign. Okay, opposite sign root, equal in magnitude but opposite in sign. Okay. So if we are getting 0 in the first column, only a single element 0, then it means either this or location of poles will be this and this, either on this line or this line, with equal magnitude but different in signs. So this kind of system, as we know that a pole is residing on the right half, क्योंकि एक पोल आपका राइट हाफ में है तो इस तरह के सिस्टम क्या कहेंगे, अनस्टेबल. ठीक है, पोल हमारा राइट में चला गया तो सिस्टम क्या हो गया, अपने आप अनस्टेबल हो गया, कुछ करना नहीं है. ठीक है, एंड इन द सेकंड केस आई हैव टोल्ड यू दैट पोल्स विल लाई ऑन दिस लाइन, पेयर ऑफ conjugate root of on imaginary axis. So if we are getting 0 element in the first column, there will be two conditions: either this condition will be possible or this condition will be possible. And now how we are going to investigate that which is the condition over here. So you can see that if the pole will lie on the right half, there will be sign change. So if sign change will occur, it means we have this condition: equal and real roots of opposite sign. And if sign change is not happening, it means we have this condition. Only two condition is possible here. And we know that in this condition, the system is given as what? Not stable. The system is marginally stable. Okay. And here I have an example of this thing, that here you can see that there is no sign change in the first column, no sign change, but still the system is not stable. It is marginally stable because we have concluded in a slide that if the poles are on this line, and are not repeated, okay, then the system is marginally stable. So if a zero occur in a column, there is no possibility that system will be stable. It is either unstable or marginally stable. वो stability से हट जाएगा, stable नहीं होगा. ठीक है, अगर zero आ गया पहले कॉलम में ना, तो वो stable होगा ही नहीं, या तो unstable होगा या marginally stable होगा. So let us stop here, and in the next class I am going to discuss another special case, that what will happen if all zero occur in a row. Means the whole row becomes 0. The whole row will become 0. What will happen then? I'm going to discuss it in the next class. Okay, so now I'm concluding here, and thank you for watching me. Thank you.